Welcome to this problem walkthrough. Today, we'll be exploring problem number 872, leaf-similar trees. This is a fascinating problem that blends tree traversal techniques with problem-solving strategies. Let's dive in and break it down step by step. To solve this problem, we need to determine if two binary trees are leaf-similar. A binary tree is defined as leaf-similar when the sequence of its leaf nodes, read from left to right, is identical to the sequence of leaf nodes in another tree. Here, the leaf nodes are those nodes that do not have any children, essentially, the endpoints of the tree. Your task is to implement a function called leaf-similar that checks whether two given binary trees satisfy this condition. The function takes in two parameters, root 1 and root 2, which represent the root nodes of the two binary trees. The expected output is a Boolean value, true if the two trees have the same leaf sequence, and false otherwise. Now let's look at an example to better understand this concept. Imagine two binary trees. In tree 1, the root node is 3, with two children, 5 on the left and 1 on the right. Under node 5, there are two more children, 6 on the left and 2 on the right. In tree 2, the root node is 5, with two children, 6 on the left and 2 on the right. Node 6 in tree 2 has a single child, also 6. When we examine the leaf sequences, tree 1 has leaf nodes 6, 2, and tree 2 also has leaf nodes 6, 2. Since these sequences are identical, the function should return true in this case. In contrast, consider another example where the two binary trees have differing leaf sequences. In tree 1, the root node is 1, with a single left child, 2, which is itself a leaf node. In tree 2, the root node is 2, with a single right child, 3, which is its leaf node. The leaf sequence of tree 1 is 2, while the leaf sequence of tree 2 is 3. As these sequences are not the same, the function should return false. This demonstrates that even if the structure of the trees may look similar, it's the sequence of leaf nodes that determines whether they are leaf-similar. For a final example, let's examine two trees with identical structures and values. In both tree 1 and tree 2, the root node is 1, with children 2 and 3. Both 2 and 3 are leaf nodes in their respective trees. The leaf sequence for both tree 1 and tree 2 is 2, 3. Since the sequences match, the function will return true. This example highlights that as long as the leaf sequences are the same, the trees are considered leaf-similar, regardless of their overall structure or size. Now, let's consider some edge cases that your solution should handle. First, if both trees have only a single node, they are leaf-similar only if the values of these nodes are the same. Second, trees with different structures but identical leaf sequences should still return true, as the structure doesn't affect leaf similarity. Third, if one tree is a subtree of the other, the output will depend solely on the leaf sequences. Finally, if the two trees have no overlapping leaf values, the function should return false. By carefully examining these cases, we ensure that our solution accounts for all possible scenarios and correctly determines whether two binary trees are leaf-similar. To begin, one straightforward approach to solving this problem is the brute force method, which involves performing separate tree traversals for each tree. The idea here is to traverse each tree independently, extract all their leaf nodes, and then compare the two resulting sequences. This ensures that the order of the leaf nodes from left to right is preserved in both trees. For implementation, we can use a depth-first search or breadth-first search to collect the leaf nodes in a list for each tree. Once we have the two lists, we simply check if they are equal. In terms of complexity, the time complexity for this approach is O, n plus m, where n and m represent the total number of nodes in the two trees. The space complexity is a bit higher because we need to account for the height of both trees, as well as the space used to store the leaf node lists. While this method is simple and direct, it does require additional memory, which can be a trade-off depending on the size of the trees. An optimized approach takes this problem a step further by traversing both trees simultaneously, which eliminates the need to store the entire sequences of leaf nodes. The key intuition here is that we can compare the leaf nodes of the two trees as we encounter them during a simultaneous depth-first search. For implementation, we perform a DFS on both trees at the same time. At each step, we check whether the current leaf node of the first tree matches the current leaf node of the second tree. If the trees have a different number of leaf nodes, or if we encounter a mismatch, we immediately return false. This approach maintains the same time complexity as the brute force method, O, n plus m, but reduces the space complexity to O, h1 plus h2, where h1 and h2 are the heights of the trees. The trade-off here is that while it reduces memory usage, implementing a simultaneous traversal is slightly more complex compared to the brute force solution. Another approach to consider involves iterative traversals, using stacks or queues instead of recursion. The intuition here is similar to the brute force method, as we still traverse each tree separately, extract their leaf nodes, and compare the sequences. However, using an iterative depth-first search or breadth-first search allows us to avoid the recursion overhead, which can be beneficial for very deep trees. For implementation, we utilize a stack or queue to traverse each tree iteratively. As we encounter leaf nodes, we extract them and compare their sequences for equality. The time and space complexity for this approach are similar to the brute force method. The main advantage is that it can be more memory efficient for deep trees, as it avoids the risk of stack overflow. However, iterative methods can be slightly less intuitive to understand and implement compared to recursive solutions. After considering the different approaches, we focus on the optimized simultaneous traversal as the chosen strategy. The key insight here is that the problem essentially boils down to comparing two sequences of leaf nodes. By traversing both trees simultaneously and comparing the leaf nodes as we encounter them, we can avoid the overhead of storing entire sequences. This insight significantly reduces memory usage. This approach is chosen because it strikes a good balance between simplicity and efficiency. It has the same time complexity as the brute force method but is more memory efficient since it does not require additional data structures to explicitly store the leaf sequences. This makes it practical for handling large trees. That said, the trade-off is that simultaneous traversal can be slightly more complex to implement and debug, especially for trees that are large or have irregular structures. To summarize, we compared three main approaches. The brute force method is simple and straightforward but requires additional memory to store the leaf node sequences. The optimized simultaneous traversal method reduces memory usage by avoiding explicit storage of sequences and directly comparing the leaf nodes during traversal. Lastly, the iterative traversal method offers an alternative to recursion, which can be more memory efficient for very deep trees, though slightly less intuitive to implement. Ultimately, the optimized simultaneous traversal approach stands out as the best choice. It balances performance and memory efficiency while directly addressing the problem's requirements without unnecessary overhead. To solve this problem, we need to determine if two binary trees have identical sequences of leaf nodes when traversed from left to right. A leaf node is defined as any node that does not have a left or right child. In other words, these are the terminal nodes of the tree. The input to our algorithm will be two binary trees, which we will refer to as root 1 and root 2. The output will be a Boolean value, true if the two trees have the same sequence of leaf nodes, and false otherwise. This sets the stage for our solution, where the focus is solely on the leaf nodes, ignoring the internal structure of the trees entirely. The core idea behind the solution is to break the problem into two main tasks. First, we extract the leaf nodes from both trees in left to right order. Second, we compare the two resulting sequences to check if they are identical. This approach works because the problem itself is defined in terms of the values in order of the leaf nodes. To achieve the extraction step, we use a depth-first search, or DFS, traversal. During the traversal, we check if the current node is a leaf node, meaning it has no left or right children. If it is, we capture its value. This systematic process ensures that we gather all the leaf nodes accurately and in the correct order. The detailed steps for extracting the leaf nodes are as follows. First, we initialize an empty list called leaves, which will store the sequence of leaf values. Next, we define a helper function, DFS, node, leaves, that performs the DFS traversal. Inside this function, we handle three cases. If the current node is null, we return immediately, which serves as our base case. If the current node is a leaf, meaning it has no left or right child, we append its value to the leaves list. Otherwise, we recursively call DFS on the left child first, followed by the right child. To extract the leaf sequence for a tree, we simply call this DFS function on the root node of that tree. Once we have the leaf sequences for both trees, we compare them using the equality operator. If the sequences match, we return true, otherwise, we return false. There are several key insights that make this algorithm effective. First, we only focus on the leaf nodes, which eliminates any need to consider the internal nodes of the trees. This simplifies the problem and reduces unnecessary computational overhead. Second, by extracting the leaf nodes into lists, the challenge of comparing tree structures is reduced to a straightforward comparison of two arrays. This is both intuitive and computationally efficient. Third, using depth-first search as the traversal method ensures that we visit every node in the tree and can easily identify leaf nodes during the process. For data structures, we rely on lists to store the leaf sequences since they preserve order, which is critical for comparison. Additionally, the recursive nature of DFS uses the call stack to keep track of traversal, making it a natural fit for tree-based problems like this one. Finally, let's discuss some optimizations and edge cases to refine our approach. One optimization is early exit. If the lengths of the two leaf sequences differ, we can immediately return false without comparing the full sequences. Another optimization is in-place comparison, where instead of storing the full leaf sequences, we compare the leaves as we traverse both trees. This reduces memory usage by avoiding the creation of large lists. Regarding edge cases, we need to handle scenarios like both trees being empty, which should return true since their leaf sequences are trivially identical. If one tree is empty and the other is not, we return false. For trees with different structures but identical leaf sequences, such as a tall left-skewed tree versus a shallow balanced tree, the algorithm should still return true. Finally, for single-node trees, the result will depend on whether their values match. These considerations ensure robustness and correctness across all possible inputs. The provided implementation solves the problem of determining if two binary trees are leaf similar by comparing their leaf node sequences. Here's the explanation. 1. The leaf similar function takes two parameters, root1 and root2, which are the roots of the two binary trees. 2. The helper function getLeaves is defined to extract all the leaf node values from a given tree. It uses an iterative approach with a stack to traverse the tree. The stack is initialized with the root node of the tree. While the stack is not empty, the current node is popped and its children are checked. If the node is a leaf, no left or right child, its value is added to the leaves list. If the node has children, they are added to the stack for further processing. 3. Once the traversal is complete, the leaves list contains the sequence of leaf node values for the tree. The getLeaves function is called twice, once for each tree, root1 and root2, to obtain their respective leaf sequences. 5. The two sequences, leaves1 and leaves2, are compared directly using the equality operator. If they are identical, the function returns true, otherwise, it returns false. This implementation efficiently handles the problem by ensuring that the leaf sequences are extracted in a left-to-right order. The iterative approach avoids recursion depth issues, making it suitable for larger trees. Additionally, the solution runs in O(n) time complexity for each tree, where n is the number of nodes, as every node is visited exactly once. The space complexity is O(h), where h is the height of the tree, due to the stack used for traversal. Here, we begin by defining a tree node class to represent nodes in our binary tree. Each tree node contains an integer value, as well as references to its left and right child nodes. We include multiple constructors to allow flexibility when creating nodes. Next, we define the main solution class, where the focus is on the method leafSimilar. This method compares two binary trees to determine if their leaf sequences are the same. To achieve this, we first collect the leaf sequences of both trees by calling the helper method getLeaves. These sequences are stored as lists of integers. Finally, we use the equals method to check if these two lists are identical. If they match, the method returns true, otherwise, it returns false. The helper method getLeaves is designed to extract the leaf values from a binary tree and return them as a list of integers. To do this, we use an iterative approach with a stack. We initialize the stack with the root node, then process nodes one at a time by popping them from the stack. If the current node is a leaf, meaning both its left and right children are null, we add its value to the list of leaves. Otherwise, we push its children onto the stack, making sure to add the right child before the left so that the left subtree is processed first. This ensures we follow the correct order when collecting leaf values. By the end of the loop, the list contains all the leaf values in the correct sequence, which we then return. To understand the concept of leaf-similar trees, let's start with an example where two trees have identical leaf sequences. Tree 1 has a root node of 3, with two child nodes 5 and 1. Node 5 further branches into 6 and 2, where 2 branches into 7 and 4. Similarly, node 1 branches into 9 and 8. For tree 2, the root node is 7, which branches into 2 on the left and 3 on the right. Node 2 has leaf nodes 6 and 4, while node 3 has a right child 8, which further branches into 9. The goal is to determine if the leaf nodes of both trees, when traversed left to right, form the same sequence. This provides the foundation for solving the problem effectively. Now, let's extract the leaf sequences from these trees step by step. Starting with tree 1, we initialize a stack with the root node, 3, and an empty list for leaves. Popping 3 from the stack, we push its children 1 and 5. Next, we pop 5, pushing its children 2 and 6. Since 6 is a leaf node, we append it to the leaves list, making it 6. Then, we pop 2, pushing its children 7 and 4. Both 7 and 4 are leaf nodes, so we append them, updating the list to 6, 7, 4. Moving on, we pop 1, pushing its children 8 and 9. Both 9 and 8 are leaves, so we append them, resulting in the final leaf sequence, 6, 7, 4, 9, 8. For tree 2, we follow a similar process and also get a leaf sequence of 6, 7, 4, 9, 8. Comparing these sequences, they are identical, so we return true. Let's now examine a second example where the trees have different leaf sequences. Tree 1 consists of a root node 1 with two child nodes 2 and 3. Tree 2 has the same structure but with the child nodes reversed, 3 on the left and 2 on the right. Extracting the leaf sequence for tree 1, we find that the leaves, in left to right order, are 2, 3. For tree 2, the extraction process reveals a leaf sequence of 3, 2. Comparing the two sequences, we see that 2, 3 is not equal to 3, 2, meaning the trees are not leaf similar. Therefore, we return false. As a final example, let's analyze the case where one of the trees is empty. Tree 1 is none, while tree 2 consists of a single node with value 1. For tree 1, since there's no root node, the leaf sequence is simply an empty list. For tree 2, the single node is also a leaf, so the leaf sequence is 1. Comparing these sequences, an empty list is not equal to 1, so the result is false. This example highlights that if one tree is empty, the trees cannot be leaf similar. With these examples, we've covered scenarios where the leaf sequences are identical, different, and where one tree is empty, helping solidify the concept of leaf-similar trees. To analyze the time complexity of our solution, we start by breaking it into 3 main steps. First, we collect the leaf nodes from the first tree using the getLeaves function. This is done through a stack-based iterative traversal, where each node in the binary tree is processed exactly once. Specifically, each node is pushed onto the stack once and popped once. For a tree with n nodes, this traversal takes n time. Next, we repeat the same process for the second tree, which also requires n time if the tree has n nodes. Finally, we compare the two lists of leaf nodes. If the first tree has m leaf nodes and the second has k, the comparison takes min m k time. In the worst-case scenario, where both trees have the same number of leaves, this step takes L, where L is the total number of leaves across both trees. Now, combining everything, let's calculate the total time complexity. If the first tree has n1 nodes and the second tree has n2 nodes, the traversal of both trees requires n1 plus n2 time. Adding the time required for comparing leaf sequences, which is L, the total time complexity becomes n1 plus n2 plus L. In the worst-case scenario, where all nodes are leaves, the number of leaves, L, will be proportional to the total number of nodes, n1 plus n2. Therefore, the worst-case time complexity simplifies to n1 plus n2. This shows that the solution scales linearly with the size of the input trees. Next, let's examine the space complexity. The space required by this solution comes from two main sources: the stack used for traversal and the lists used to store the leaf sequences. During the iterative depth-first traversal in getLeaves, the stack holds nodes temporarily. In the worst case, if the tree is completely skewed, the stack can grow to hold all nodes, leading to O(h) space usage, where h is the height of the tree. For a balanced binary tree, the height is log n, while for a skewed tree, the height is n. Since we process both trees, the stack contributes a total of O(h1 plus h2) space, where h1 and h2 are the heights of the two trees. Additionally, we store the leaf nodes in two separate lists, leaves 1 and leaves 2, which together require O(m plus k) space, where m and k are the number of leaf nodes in each tree. In the worst case, all nodes are leaves, so the space required for the lists is proportional to O(n1 plus n2). Combining these components, the total space complexity of the solution is O(h1 plus h2 plus m plus k). In the worst case, where both trees are skewed and all nodes are leaves, the height and the number of leaf nodes for each tree are proportional to the total number of nodes. As a result, the space complexity simplifies to O(n1 plus n2). Comparing this to a naive approach where recursive DFS is used for traversal and all nodes are stored, our solution is significantly more efficient. The naive approach would require O(n1 plus n2) space for storing all nodes and additional time for comparing the full lists of nodes. By focusing only on leaf nodes, our solution optimizes both space and time, especially when the trees have a large number of internal nodes compared to leaves. Finally, let's look at the best, average, and worst-case scenarios. In the best case, both trees are empty, requiring no traversal, and the time and space complexity is O(1). For the average case, where the trees are balanced binary trees with a mix of internal and leaf nodes, the time complexity is O(n1 plus n2), and the space complexity is O(h1 plus h2), as the traversal depth is limited to the tree height. In the worst case, the trees are skewed, and all nodes are leaves. Here, the time and space complexities both become O(n1 plus n2). Mathematically, the solution's time complexity is derived from processing each node exactly once during the traversal, contributing O(n1 plus n2). The comparison of leaf sequences adds O(l), but since L is bounded by n1 plus n2, the total time remains O(n1 plus n2). Similarly, the space complexity is determined by the stack and the leaf lists, which also simplifies to O(n1 plus n2) in the worst case. When solving this problem, there are several common mistakes to watch out for. First, it's easy to misidentify what qualifies as a leaf node, especially in edge cases like a tree with only one node. Remember, a leaf node is any node that has no children. Another frequent issue is incorrectly comparing the leaf sequences. Some solutions focus on checking the lengths of the sequences first, but this problem requires the sequences to match exactly in both content and order. Inefficient traversals are also a problem. For example, repeatedly traversing the same subtree can significantly increase time complexity. Instead, aim for a single pass to extract all the leaf nodes. Additionally, failing to handle edge cases can lead to runtime errors. You need to account for scenarios like one or both trees being empty, trees with only one node, or imbalanced trees. Finally, avoid assuming that the trees are balanced. Such assumptions may lead to incorrect expectations about the depth of traversal or overall time complexity. Always ensure your solution works for any tree structure. Now, let's discuss some insights that are particularly relevant for interviews. This problem is a great example of comparing tree properties. Recognizing this pattern can help you tackle related problems, like detecting subtrees or checking if a tree is symmetric. Interviewers may also look for solutions that optimize space usage. For instance, instead of explicitly storing the leaf sequences, you could design an approach that uses O(h1 plus h2) space, where h1 and h2 are the heights of the trees. Another point to consider is the trade-off between recursive and iterative solutions. Recursive solutions are often more intuitive for tree problems, but they can lead to stack overflow in cases of very deep trees. Being able to discuss this trade-off demonstrates a solid understanding of algorithm design. Lastly, interviewers will likely appreciate your ability to identify and handle edge cases. This shows that you're thorough and have a deep understanding of tree structures. To build on these ideas, consider exploring related problems like comparing leaf sequences, checking if two trees are identical, testing for symmetry in a tree, or determining if one tree is a subtree of another. Let's explore some alternative approaches to solving this problem. A straightforward method is the brute force approach, where you perform separate traversals for both trees, extract their leaf nodes into arrays, and then compare the arrays. While this method is simple to implement, it requires n plus m space, where n and m represent the number of nodes in the respective trees. A more space-efficient option is to use a single traversal with inline comparison. By leveraging a generator to yield leaf nodes during traversal, you can compare the nodes lazily, avoiding the need to store the entire sequences in memory. However, this approach can be harder to debug and implement. Another alternative is the iterative approach, which involves using two stacks to perform a depth-first search on both trees simultaneously. This allows you to compare leaf nodes as they're discovered. While this method avoids recursion, making it safer for very deep trees, it can be less intuitive and may require more code. Each of these approaches has its own trade-offs, and the best choice depends on the constraints and requirements of the problem you're solving. Great job! Today, we explored the leaf-similar trees problem and broke it down into manageable steps. Remember the importance of mastering traversal techniques and optimizing for time and space. Thanks for watching, and don't forget to like, share, and subscribe for more coding insights. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!